Unit 4, Solutions and Solubility, Section 8.1, The Importance of Water. Take a look at this diagram of water. Remember that it is a polar molecule that has a slightly positive end on each of the hydrogen sides and a slightly negative end on the oxygen side. In Chapter 3, you learn that the OH bond in the water molecule is highly polar. The difference in electronegativity is 1.2. Due to the polar OH bonds and asymmetrical shape of water, it's considered a highly polar molecule. Water molecules undergo the strongest type of intermolecular force called hydrogen bonds. Hydrogen bonds are unusually strong intermolecular forces between a hydrogen polar molecule to a highly electronegative atom such as oxygen, nitrogen, or fluorine in another molecule. Hydrogen atoms develop a partial positive charge, and the highly electronegative atom develops a partial negative charge. There are two main reasons for hydrogen bonding in water. Number one, the large difference in electronegativity between hydrogen and oxygen atoms. And number two, the small size of hydrogen, which means that the positive pole is highly concentrated. It is therefore strongly attracted to the negative pole of the nearby molecule. If a molecule can act as a donor or an acceptor, its intermolecular forces must be strong enough to hold the molecules together. The strength or stickiness of this interaction increases as the size or polarity of the molecules increases. It is the hydrogen bonding that provides the additional stickiness to hold water molecules together as a liquid up to almost 100 degrees Celsius. Please try practice problems in the textbook and any LMS quizzes that are assigned. In Table 2, we see the unusual properties of water resulting from hydrogen bonding. The first property is the high melting and boiling points. This permits water to exist as a liquid at room temperature, and it keeps body fluids liquid over a large range of temperatures. Water expands when cooling from 4 degrees Celsius to 0 degrees Celsius. This expansion causes ice to float, and it causes water to freeze from the top down, allowing life to continue below it. Water has a high surface tension. This pulls water into round droplets. It allows small insects to walk on water. Water shows the ability to exchange thermal energy with little change in temperature. This enables water to absorb a great deal of thermal energy for a small increase in temperature and to release a great deal of energy for a small decrease in temperature. This has a moderating effect on temperature changes in organisms and the environment. Water shows the property of having the inability to mix with nonpolar compounds. This enables organisms to retain water because of a waterproof coating, for example, wax on leaves. It also allows organisms to store nonpolar substances, such as fats and oils. In Section 8.2, we're going to look at solutions and their characteristics. This is a reading assignment. I want you to read pages 376 to 379 and complete the following questions. (8.5) Solubility and saturation. Table 1 shows the solubility of common solutes in water at 20 degrees Celsius. And you'll notice that the various compounds have various solubility. The amount of a substance that can completely dissolve in 100 grams of water at 20 degrees Celsius. Let's define some important terms. A saturated solution is a solution that contains the maximum quantity of a solute at a given temperature and pressure. An unsaturated solution is a solution in which more solute can dissolve at a given temperature and pressure. And a supersaturated solution is a solution that contains more than the maximum quantity of a solute that it should hold at a given temperature and pressure. Take a look at this figure. This figure shows the solubility in grams per 100 grams of water of various substances at various temperatures. And we can use this table to determine the type of solution that will form for a given amount at a given temperature for different compounds. Points directly on the curve represent a saturated solution. Points below the curve represent unsaturated solutions. The vertical difference between a point below the curve and a point on the curve represents the additional mass of solute per 100 grams required to saturate the solution at that temperature. Points above the curve represent supersaturated solutions, and the vertical difference is a point above the curve and a point on the curve, which represents the mass of solute per 100 grams of water that will crystallize out of the solution at that temperature. Note, supersaturated solutions are prepared by dissolving a solute in water at high temperature where its solubility increases and then allowing the solution to cool. Any additional amount of solute after cooling will cause the excess solute to crystallize out of the solution. Let's use the graph for solubility to answer the following questions. Question number 1. Calculate a solution that contains 60 grams per 100 grams of water of potassium nitrate at 40 degrees Celsius as a saturated, unsaturated, or supersaturated solution. So let's find potassium nitrate at 40 degrees and see if the amount at 40 degrees is greater than, equal to, or less than 60 grams per 100 gram. So we're looking for potassium nitrate at 40 degrees. This is the curve for potassium nitrate. And at 40 degrees, this is the curve for potassium nitrate. And at 40 degrees, in order to be a saturated solution, you would have to have roughly 65 grams per 100 grams of water. So if we only add 60 grams, then this will be an unsaturated solution because it's less than 65 grams per 100 grams of water. Question number 2. What mass of solute is required to saturate a solution containing 10 grams per 100 grams of water of sodium chloride at 30 degrees Celsius? So the solution already contains 10 grams. We need to know how much more we have to add at 30 degrees of sodium chloride in order to make it saturated. Let's find out the saturation level of sodium chloride at 30 degrees. This is the curve for sodium chloride. And at 30 degrees, the saturation is about 38 grams per 100 grams of water in order to be saturated. If the solution already contains 10 grams, (38 grams) minus the 10 grams it already contains, we need to add 28 grams of NaCl in order to saturate a solution. Question number 3. At what temperature does a solution containing 50 grams of potassium chlorate become saturated? So let's find potassium chlorate and see at what temperature 50 grams will be saturated. So here is the curve for potassium chlorate. And we're going to see 50 grams where it connects with potassium chlorate. And it looks like it will be saturated between 90 and 95 degrees Celsius. Now let's take a look at the solubility curves of gases. Unlike with solids, the solubility of gases decreases as the temperature rises. So as temperature increases, solubility decreases. The trend in solubility for oxygen means that cold water contains more oxygen than warm water. Let's define pressure. Pressure is the force applied to a unit area. Pressure has little effect on solids and liquids because these states are not very compressible. Gases, however, are significantly affected by changes in pressure. In particular, the solubility of a gas in a liquid increases as the pressure of the gas is increased. This is important for aquatic animals. The lack of oxygen in warm water can be extremely stressful on fish, equivalent to suffocation. This explains why fish are more likely to be found in deeper, cooler water than near the surface. This also explains soft drinks. Soft drink manufacturers use the property of pressure to dissolve far more CO2 in pop than it can hold at normal atmospheric conditions. Chilling the drinks while they are being carbonated also helps more of the gas dissolve. There are no gas bubbles in a sealed bottle of pop because the pressurized gas above the surface keeps the CO2 dissolved in the liquid. Opening the bottle reduces the pressure. This decreases the solubility of CO2, causing the sudden increase or release of carbon dioxide bubbles. The release of bubbles proves that pop contains more dissolved carbon dioxide than it should. A carbonated drink is an example of a supersaturated solution. Please try any homework problems assigned and any LMS quizzes on this section. Section 8.6, Concentration. The amount concentration is given the symbol lowercase c. It's equal to the amount in moles of solute dissolved per liter of solution, and the unit symbol is moles per liter. A stock solution is a concentrated solution that is used to prepare dilute solutions for actual use. The concentration of stock solutions depends on the type of stock acid. For example, hydrochloric acid has a stock acid amount concentration of 12 moles per liter. The stock acid nitric acid has an amount concentration of 16 moles per liter. Sulfuric acid has an amount concentration of 18 moles per liter for the stock acid. We can calculate the amount concentration by taking the amount of solute in moles and dividing by the amount of solution in liters. In symbols, we say C is equal to N over V. C is equal to N over V. And we can write this in our equation triangle. Let's try a sample problem, calculating amount concentration. Sulfuric acid is a solution of hydrogen sulfate dissolved in water. When concentrated, it is extremely corrosive. A 25 ml sample of concentrated sulfuric acid contains 44 grams of hydrogen sulfite. Calculate the amount concentration of the solution. Amount concentration is equal to the number of moles divided by the volume. The volume is given in this question. It's 25 milliliters, which is 25 times 10 to the power of negative 3 liters, or in proper scientific notation, 2.50 times 10 to the power of negative 2 liters. Now we need to find the number of moles of H2SO4. We can find that using our equation for amount. The number of moles is equal to mass divided by molar mass. So we need the mass of H2SO4 divided by the molar mass of H2SO4. In the question, they tell us there are 44 grams and the molar mass of H2SO4. If you use your periodic table to find the molar mass of each of the elements in the chemical formula, we end up with 98.08 grams per mole. That gives us an amount of 0.4486 moles of H2SO4. So let's go over here and calculate the concentration. Concentration equals number of moles divided by volume. Punch this into our calculator. And we get 17.9 moles per liter. Let's use the equation to calculate volume. Household chlorine bleach is a 0.067 mole per liter solution of sodium hypochlorite, NaClO. What mass of sodium hypochlorite is required to prepare a 225 milliliter sample of bleach? We know that concentration is equal to number of moles divided by volume. We can rearrange this to solve C is equal to N over V. Solve the amount of volume. If we cover up the volume, we are left with number of moles divided by concentration. The volume in this question is 225 milliliters. That is 225 times 10 to the power of negative 3 liters, or 2.25 times 10 to the power of negative 1 liters in proper scientific notation. Now the number of moles is equal to concentration times volume. The concentration is 0.067 moles per liter. And the volume we just calculated was 2.25 times 10 to the power of negative 1 liters. If we punch this in, we end up with 0.01508 moles. If we were to make the solution, we would need to know how much mass to add. How much mass of sodium hypochlorite would we add to 225 milliliters We know that mass can be found using the amount. The number of moles is equal to mass divided by molar mass. So the mass is equal to the number of moles times the molar mass. We just determined the number of moles, and we're going to multiply this by the molar mass of sodium hypochlorite, which is 74.4 grams per mole. If we punch this into our calculator, we end up with 1.12 grams of NaClO. Please try any practice problems in the textbook, read over the section, and any LMS quizzes pertaining to this section. 8.7, preparing dilutions. Recall that the amount concentration is equal to the number of moles divided by volumes. We can dilute concentrated solutions into dilute solutions using the dilution equation. The dilution equation says the concentration of concentrated solutions times the volume of concentrated solutions equals the concentration of diluted solutions times the volume of diluted solutions. We sometimes see this equation as written as C1 V1 equals C2 V2. Let's try an example. Determining amount concentration. What is the final concentration when 250 milliliters of a 16 mole per liter nitric acid solution is diluted to 4.5 liters? So we have the concentration of the concentrated solution, 16.0 moles per liter, and the volume of the concentrated solution, 250 milliliters, or 0.250 liters. We have the volume of the diluted solution is 4.5 liters, and we need the concentration of this new diluted solution. So we know CVC equals CdVd, and what we want to find is CD, the concentration of the diluted solution. So we're going to divide both sides by the volume of the diluted solution, and we end up with concentration of the concentrated solution times the volume of the concentrated solution divided by the volume of the diluted solution. Let's sub in these values. We have 16.0 moles per liter times 0.250 liters over a new volume of 4.5 liters. If we punch this into our calculator, we get a concentration of the diluted solution to be 0.89 moles per liter. Please read over this section, try any practice problems assigned, as well as any LMS quizzes on this section. (8.8) Concentrations and consumer products. The concentration of consumer products can be written in percent volume per volume. This is used for liquid-liquid mixtures. We could also have percent weight per volume. This is for solid liquid mixtures. And finally, percent weight, and this is used for solid liquid or solid mixtures. And there are equations for calculating each of these different types of concentrations. Sample problem number 1, calculating volume from percent volume per volume. The concentration of ethanol in a 750 milliliter bottle of wine is 13.5% volume per volume. Assuming that the wine has the same density as water, calculate the volume of ethanol in the bottle. Let's look at our equation for the concentration of volume per volume. The concentration of volume per volume is equal to the volume of the solute divided by the volume of the solution times 100%. In this question, they give you the concentration of alcohol, 13.5%, and they give you the volume of the solution, (750 milliliters), and we want to calculate the volume of the solute, ethanol. We can rearrange this equation, and the volume of ethanol is equal to the concentration of the solution times the volume of the solution divided by 100. That's 13.5% times 750 milliliters divided by 100. If we leave the volume in milliliters, our answer will be in milliliters. And we end up with 101.25 milliliters of ethanol in 750 mils of wine at 13.5% volume per volume. Let's try a second example where we calculate the volume of a solution from the mass of a solute. Glucose, C6H12O6, is used to prepare intravenous feeding solutions. What volume of a 5% weight per volume glucose solution can be prepared using 125 grams of glucose? Let's take a look at our equation. The concentration, weight per volume, is equal to the weight of solution, or solute rather, divided by the volume of solution times 100%. We're given a concentration of 5%. We're given a weight of glucose of 125 grams. And we need to find the volume of solution required. We can rearrange this equation. The volume of solution is equal to the weight of glucose divided by the concentration of glucose in weight per volume times 100. That's 125 grams divided by 5% times 100. Punch this into our calculator. And we end up with 2,500 milliliters of solution. Let's look at an example where we calculate dilutions using percent concentrations. What is the final concentration when 125 milliliters of a 30% weight per volume hydrogen peroxide solution is diluted to 2 liters? So in this example, let's list what we have given. We have an initial volume of 125 milliliters, or 0.125 liters. With an initial concentration of 30% weight per volume. And we're going to dilute this to 2 liters. And we want to know the final concentration. So initial concentration times initial volume equals final concentration. It's final volume. We can solve for the final concentration, divide both sides by V2. And the final concentration is equal to C1 V1 over V2. That's 30% times 0.125 liters divided by 2 liters. And remember, write 30% as a decimal. So we'll do that by divided by 100. So we end up with a concentration of 0.019% weight per volume. Extremely low concentrations are found with scientists working in the medical or environmental fields, and they express these concentrations as amount concentrations or percent concentrations, and that would give them very awkward numbers to work with. So for this reason, very dilute concentrations are often expressed in either parts per million, parts per billion, or parts per trillion. Let's look at an analogy. 1 part per million is equivalent to 1 drop in a bathtub full of water, or 30 seconds out of a whole year. 1 part per billion is equivalent to 1 drop in 250 full barrels, or 3 seconds out of an entire century. And 1 part per trillion is 1 drop in 20 Olympic-sized pools, or 3 seconds out of 100,000 years. For example, a bottle of water may contain sodium ions at a concentration of 36 parts per million. This means that there are 36 parts of sodium for every million parts of solution. This concentration is so dilute, you would have to drink 56 half-liter bottles of water to consume only 1 gram of dissolved sodium ions. Let's calculate calculating concentration in parts per million. A 1.5 liter sample of pool water contains 4.5 milligrams of chlorine. Determine the concentration of chlorine in parts per million. To find the concentration in parts per million, we need the mass of the solute divided by the mass of the solution times 10 to the power of 6. The mass of the solute is 4.5 milligrams. And we need the mass of 1.5 liters of water. The mass of 1.5 liters of water is 1.5 kilograms, or 1.5 times 10 to the power of 3 grams, or 1.5 times 10 to the power of 6 milligrams. So we have 4.5 milligrams of chlorine divided by 1.5 times 10 to the power of 6 milligrams of water times 10 to the power of 6. Punching this into our calculator, we end up with 3 parts per million of chlorine. Please try any practice problems. Don't forget to read over this section. As well, try any LMS quizzes relating to this section.